On the free body diagram, I included these external forces from the pulleys acting on the two, or the ropes acting on the two pulleys at this point and this point. Again, it's going to turn out the radii don't matter of the pulleys. I'll just call it R for the moment. When you actually go through the equation step, you'll see that they kind of cancel each other out the way that this is working. At A, we have a thrust bearing. At B, we have a journal bearing. So from your free body diagram, what else do you need to go on this free body diagram? Yeah.
AX, AY, and AZ.
Right, so 3 reactions at A, 3 force reactions. I forget if this says it. Okay, they tell us that the journal bearings at A and B, I must have reworded it but not got rid of that part. We're going to make the assumption they're properly aligned. So we only have 3 force reactions at A. I called it a thrust bearing at the top. I must have not gotten rid of it at the bottom. And at B, we have a journal bearing. So what forces are we going to have at B? Right, BX and BC. On the free body diagram, we come out with 5 unknowns, which is okay. We can have up to 6 unknowns if it's statically determinate. And we're going to get to statically indeterminate problems in a couple of weeks where we can have, it's okay if we have more unknowns than we have equilibrium equations, because we're going to develop methods to get more equations outside of just equilibrium. So this should be your complete free body diagram for the external picture. Yeah.
Should the distance between the two pulleys be like 0.35?
Right, I misread my notes here. Right, that's a 3. It was very small. Yeah, the 0.25 plus the 0.1. From the external picture, we can get 6 equations. For our 6 equations, they won't all be linearly independent, but we'll get 5 linearly independent equations for the 5 unknowns. I won't go through those steps now. I will give you the numbers that we get out of them. So X, we get negative 250 newtons. AY, we're going to get 0, and AZ, 360. BX is negative 750, and BZ, we get 240. To get those, you would do the sum of forces X, Y, and Z. You would do the sum of moments around a point, probably A, and then we're going to get the 5 linearly independent equations. One of them we do get, if we do the sum of moments around A, when you go at the coefficients in front of J, you just get 0 equals 0. So that's why we only have 5 linearly independent equations. Once we have the external forces, then we can draw the internal picture, cutting at C. In my picture, I chose to take everything from C to A. But again, you could take C to B. I just chose this because it would be really just easier to look at this way. So I cut through the shaft at C. I have the pulley. I have the external forces that were acting at A in the right directions from what I assumed in my first picture. So the 250 is actually in the negative X direction. The AZ is in the positive Z. And AY I don't need to draw since it was 0. At that cut surface, I now will have those 6 internal forces or internal loads that I have to draw. Our assumptions are that the internal normal force comes out from the outward normal. So P sub C is in the positive Y direction because it's the outward normal from the cut. If you had taken the other half of the shaft, then your internal force would be pointing in the negative Y direction, since that would be the outward normal from the cut. So for the internal normal force and the internal torsion, they're only based on the outward normal from the cut surface, not your global coordinate system. Once I determine the direction of my internal normal force, I now know the direction that I'm assuming my torsion is in will be positive around that axis determined by the internal normal force. So I'm going to assume that T is positive around that PC axis. Again, those two things are always based on the outward normal of your cut surface. Now, for our components of our shear force, we're going to use our global coordinate system since it's set up nicely here. So we're going to say a component of the internal shear is going to be along the X direction, positive X. And a component of it is along the positive Y direction. Positive Z direction. In actuality, the shear force is somewhere in that plane, in that XZ plane, in one direction. But if we break it down into these components, it makes the math easier to solve. So some of it is in the X, some of it is in the Z. I'm making the assumption that both components are positive. That could be incorrect, but I'll solve for that when I go through the math. Now again, there'll be an internal bending moment that's going to be around some axis in the XZ plane, but that too I can break down into components. So I'll say some of it is around the Z axis, MZ, and some of it is around the X axis, MX. 2 components of bending moment, 2 components of shear force, the internal normal force, and the internal torsion T. Do sum of forces, do sum of moments, you get these new 6 unknowns. You can solve for those with those 6 new equations that we get. In the interest of time, I'll just give you the numbers we get out of it, and you can check those later. Internal normal force, we get 0. Internal torsion for this problem, we also get to be 0. Component of shear force in the X direction, we get 250 newtons. Positive according to my assumptions. VZ, we get 240 newtons. Positive according to my assumptions. Component of the bending moment around the X, 108. And around the Z, 138.